Okay, hello everyone, and recording has started. Um, let's start today's meeting with some topics that relate to the current homework assignment. We talked about this last time. A crucial mathematical object, which is a big part of the story here, is this function f of x. And what we want to do today, as we talk about this function, which is relevant for the current homework assignment, we want to bring in some of the fundamental themes of our course and take this opportunity to see how those themes occur here. Things like composition of functions. We've talked about functional composition. When you insert one function into the input of another function, this is very important. We'll see how that occurs here, and other things such as the chain rule, right? So the chain rule and functional composition are really crucial things for our course. Let's talk about how that relates to this material from chapter 12. Of course, chapter 12 not on the final exam. So first of all, let's talk about the functional composition. When we talk about functional composition, we're talking about constructing new functions by taking one function and inserting it into the input of another function. So functional composition. So the verb here is to compose, right? Compose. So how did we use functional composition in the past, and how is it relevant to the current homework assignment? So let's have a look at those two topics like so. We've had a lot of examples here in our course. A typical example would be Lagrangian mechanics. You have a Lagrangian, and the crucial thing here with the Lagrangian is to understand that it is a function with multiple variables as the input. So let's write it like so. Okay. For 1 degree of freedom, you might write a Lagrangian like this. And we'll compare this with chapter 12, logistic map. Okay, so anytime we have a comparison like this, it's useful, you know, it helps to give us different perspectives, and we get a deeper understanding. So of course, when we write a Lagrangian like this, this is understood that we have 1 degree of freedom. Okay. For our discussion of functional composition, 1 degree of freedom is perfectly adequate. We could, of course, go through this with multiple degrees of freedom. So the first observation is to appreciate the existence of this function, right? The existence of this function, apart from any decision you make for what to insert, okay? So this is a mapping as we've drawn it here. Okay, this is a mapping from R3 to R. We have 3 independent variables. That's the really important thing here. 3 okay, 3 independent variables. 1, 2, and 3. Okay, and the crucial concept, of course, which we've discussed, is the so-called classical state space. What does it mean in classical physics when you talk about the state of a system? Well, you must specify position type information and velocity type information, right? The evolution of the system is then, the subsequent evolution is determined by that, the time evolution. So we've talked about the classical state, and at this point in the discussion, we have a well-defined function. Of course, we know a huge amount of grief has been caused by the notation. the idea that we use Q and Q dot, right, causes a lot of confusion every semester, okay? Alternative would be, say, Q for this coordinate and V for velocity. Then the variables would be Q, V, and T, and that helps to understand that we're thinking of 3 independent variables, okay? So the connection we want to make here is earlier when we talked about the logistic map, we wanted to really emphasize the existence of this function f. And notice we have the function f here without any further decoration. There's no need to put a subscript on the little n. This function exists. In fact, this is a function you can describe verbally, as we'll illustrate with the following just standard English phraseology here. The function evaluated for some value is the product of the value times 1 minus the value times a constant r, okay? So that's a prescription how to produce an output number from the input number. And some computer languages allow this. You don't have to give the input a name. Notice here the input is given the name x. But you see x is kind of just a placeholder. And some languages have their own notation, so you don't have to commit to any sort of name for the variable. They have this level of abstraction, all right? So again, that level of abstraction was illustrated when I said the function evaluated for some input value is the input value times 1 minus the input value times a constant r. So I never had to name that input variable. So that's useful to understand the existence of this function as a prescription, right? It's a rule for producing an output value given an input value. Okay, so that's that function f. That one happened to be a function from r to r, all right? Now the Lagrangian, of course, is a function from, for this 1 degree of freedom problem with a time-dependent Lagrangian, it's a mapping from R3 to R, okay? Now the functional composition occurs when you insert the orbit, okay? So let's emphasize that this is logically distinct, right? This first part of the discussion, this was a well-defined, self-contained discussion of a function of 3 variables. Now, if we choose to insert all right, in classical mechanics, we like to use this phrase orbit for any solution. It doesn't have to be a nice elliptical orbit. The emphasis here is that we have a function of time. So when we say the orbit, notice now Q is a function of time. Now Q is the dependent variable and T is the independent variable. All right. So I'm emphasizing here with this bracket structure that this is a separate thought, right? We're going to insert this orbit into the Lagrangian, and now we must insert Q of T here, Q dot, which now is the derivative, okay? So now we have a function of time. Okay, so the resulting construction gives us a function of the time t only. We have the Lagrangian okay, so that's the resulting construction. It is now a function of a single variable t. In other words, a user would provide some value for t. Based on that value, you look up the value for q, you look up the value for the slope, and you insert the value here. Okay, so this is a mapping. You input the time t measured in seconds, you output Lagrangian measured in joules, right? It's an energy. It has dimensions of energy. Okay, so, and then the crucial thing is if you want to differentiate this, you talk about the total time derivative. Okay, and we've had some very nice theorems along these lines. The total time derivative All right. Again, this is a logically distinct thought. When you see this ordinary d, that's a regular lowercase d, that's a regular lowercase d, etc. When you see that, it means we are doing the total time derivative. This is not a partial derivative, right? And the language is very clear. Total, that word makes it clear we're not talking about a partial derivative, we're talking about a total derivative. That means you insert, you must do the functional composition. So this is the functional composition. Let's draw a big arrow down here, functional composition. Here we go. Big arrow all the way. And now I'll move the paper. Okay, that was the functional composition. The total time derivative, we must look for any occurrence of the time t and then use the chain rule. So here's a t. That means we'll compute a partial. Okay, and when we compute this partial, we invoke the original definition, partial L, partial Q. So you see the notation, that's the stylized lowercase d, not a lowercase delta. It's a partial derivative. So here, we're using the original definition for the Lagrangian. That's what we had up here. You see, we had a mapping. This was a multivariable calculus construction, right? So this is what's going here. Right, another big arrow. We're invoking the original definition. We had 3 independent variables. You've got 3 independent variables. If you're differentiating with respect to one of them, it's a partial derivative. Okay, and then the chain rule tells you you must multiply by the derivative. That's Q dot. We got another term here. And as you know, this is going to be a partial L, partial Q dot. Again, that's this thing. Multiply by the derivative. Chain rule says you must multiply by the derivative. And now here's just a t. So plus partial L, partial t. Okay, so that's a reminder because we're using those same foundation skills here with the logistic map. And we'll talk about a few examples. If you look at period 2, these so-called 2 cycles, okay, we'll define a function g of x equaling f of x. Okay, so obviously there's a slight difference here. We are doing functional composition. We've inserted one function into the input of another function. In this case, it happens that both the functions are f. Okay, this is good in the sense that it challenges us. We must wake up and smell the coffee to really appreciate what's going on here. But let's first appreciate the construction, right? A user of this function g provides a value x. Here's a prescription. First, you plug x into f, that returns a value. That returned value gets inserted into f once again, like so. Okay, and so that's the functional composition, like so. Okay, now let's talk about the derivative. And armed with our good understanding of the chain rule, this should be no problem. So the derivative here, this is a function of one variable, so we're very safe in just writing g prime of x. We use the prime when we have a derivative of a function of a single variable. Okay, for extra clarity, let's write dg dx, and that's an ordinary d. Okay, now here's where things get a little tricky. The chain rule says, okay, because we have the functional composition, the chain rule, first thing you got to do is differentiate this outermost function. In this case, the outermost function is f. So differentiate f. And then evaluate that derivative at this point. And the value there is f of x. And then the chain rule says you must multiply by the derivative of what's inside here. and that's evaluated at x. So this is kind of funny. If you were to suppress the arguments, look how funny this equation is. With suppressed arguments, g prime is equal to f prime, f prime. Okay, this is very streamlined notation. Remember, when we suppress the arguments, it saves us some time writing the formula, but there's always a danger of confusion because we don't have all that information. We shouldn't just write f prime squared, because this f prime is evaluated right. That first factor is evaluated at f of x, which is some value, and the second factor is evaluated okay. So that's the construction. Let's take a second to talk about period 3. And the reason I mention this is, you know, in the current homework assignment, we are studying several figures in the text very intensively. Figure 12.41, figure 12.44. Now, these are wonderful figures. Right, let's have a quick look here. So around about page 500, and then a few pages further. Okay, so here's this remarkable picture. And one thing we're going to really investigate in today's lecture is we just want to ponder how amazing it is that this diagram occurs in our analysis of this logistic map, which was a discrete mapping, right? Using that lowercase f function that we just talked about. Remarkable rich structure that emerges, okay? Basically, the same picture emerges for the dynamical system that we introduced last time, the damp-driven pendulum. The structure of this picture is identical, and in particular, there are certain special values here on the r-axis, and their behavior is going to be identical to certain special values. We'll have a horizontal axis for the dynamical problem, which is a control parameter. And so there's this universality in chaos, right? This period doubling route to chaos is one of the most remarkable things. Again, these were discoveries of the past few decades. So this is more of a modern era, as opposed to most classical mechanics was done a couple hundred years ago, all right? So the modern era with the study of chaos, and this is one of the amazing results here, this universality in chaos. You have drastically different problems exhibiting the same, not every chaotic system has this period doubling route to chaos, but the ones that do exhibit this universality. Now notice here, here it's stated in text, period 3, and the word 3 is written out. Period 3, okay? It's useful to take a look at that since this does figure prominently into what we're doing. It's very visible here. When we say period 3, what part of the diagram are we talking about? Well, I'll need a sharp instrument to point, and I think I will use this pen cap as a precision pointer, okay? You see right there at around 3.82, if r, here's the r-axis, if r is 3.82, let's draw a vertical line and see what we have there. There's a value here. It's a little less on the vertical axis, a little less than 0.2. There's another value right around 0.5, and then there's another value about 0.96, okay? And so if you have r equal to, it's approximately 3.82, and I did upload a document earlier today to the Homework 11 folder that talks about this point. In general, period 3 is very difficult to analyze. So what we want to do today is an opportunity to review our understanding of functional composition. Let's take this opportunity to understand what's going on with period 3 in this context. Okay, we just talked about period 2. And what does the 2 mean? Well, at the most literal level, the 2 is the number of f's. Okay, here's an f, there are 2 f's, all right? And so if you find a fixed point of this mapping G, that means there's some value x. you apply the function f to that value, you get a different value. And then you apply the function f to that value, you get the same value. So period 2 are fixed points of this. Very similar construction here, period 3. Okay, for period 3, it's a nice collection of parentheses. What we're doing here, the story begins here with this number x. We apply the function f, so f of x, you see there's one layer of parentheses there. This produces a value. That value is inserted to f because this f, together with this parenthesis and this middle parenthesis over here, that's our second application of the function f. And then that return value is once again inserted into the function f. So this is functional composition on a grand scale. A useful exercise here is to appreciate this produces an 8th order polynomial. Okay, that's remarkable. Why is this an 8th order polynomial? Well, what happens here, remember, the function f, this is a quadratic, here's f, right? This is a quadratic polynomial. If you expand this, there's a linear term, x to the first power, and there's certainly a quadratic term here, x squared. The coefficient is minus r, right? There's the minus sign, there's the r. So this is a quadratic polynomial. That's important to appreciate here, okay? So you have a quadratic polynomial. Then at the first stage of functional composition, you take that quadratic polynomial, you insert it into f. So the input into the function f is already a quadratic polynomial. F is a prescription. Remember we described it verbally. It's a prescription whereby you compute a new number, and one of the steps involves squaring the input. So at that point, you have a 4th order polynomial, okay? So notice that this g of x is a 4th order polynomial. Okay, and I put that here as a little remark. I understand it's hard to read because I wrote too small. But this g of x is a 4th order polynomial, okay? And this one here is an 8th order polynomial. So if you're looking for a fixed point, we want to solve this equation, all right? And there are some remarkable results from classical mathematics. You can solve the most general 4th order polynomial equation, at least in the complex plane. You can find the roots using elementary functions. When you go past 5th order, in general, there's no solution in terms of elementary functions. Now, what I did today, I uploaded a document. It's kind of an optional document because we are getting a little far afield here, but we just want to appreciate from the perspective of functional composition, this is an 8th order polynomial. Now, you can factor it rather easily. It turns out you can factor it into 2 small polynomials, very low order, and then a 6th order polynomial, okay? So when you try to solve, we want to solve this equation. It's a rather challenging polynomial equation. We'd like to solve it. You can remove a certain kind of elementary roots, but the remaining problem is a 6th order polynomial. In general, that's very difficult to solve. There's no, in general, when you're looking at 6th order polynomials, there's no simple formula like we have the quadratic formula for 2nd order polynomial equations. Okay, so the objective here is to appreciate the structure. I did upload an optional remark this morning. The point is for special values of R, you can write down solutions, okay? So that's an optional remark. Again, we're getting a little far afield, but the point is, one of the things we've seen throughout this course is that our formulation of classical mechanics, we very quickly run into challenging mathematical problems. Okay, we've seen that throughout the course. whether it's a differential equation or an algebraic equation. These are algebraic equations. So that's one of the kind of meta themes of the course, that mechanics problems, they rapidly run into, we have a whole world of interesting math problems that has emerged over the course of this summer session. So this structure is part of that bigger picture. Now our emphasis today is to understand and appreciate this universality in chaos. So we do have this onset of chaos in the logistic map, which you're studying on the current homework assignment. And then we have a dynamical system, right? A completely different system. It's a dynamical system with a continuous time axis, all right? So the universality is really the remarkable theme here. Okay, so yeah, so this has been an opportunity to review the chain rule, right? The chain rule is so important to us. Again, the chain rule tells you how to compute the derivative of a function that is constructed by functional composition. So we use the chain rule here to get G prime. The best way to look at it is this one here. If you suppress the arguments, it's mightily confusing. Okay, and we use the chain rule here. This was in a multivariable context, but again, this was the chain rule. So functional composition and the chain rule, those are really amongst the most foundation concepts here in our course. Okay. So last time we were talking about the similarities. Okay, it was useful for several objectives to have this comparison, right? This was something we talked about at the end of our last meeting. We got chapter 12 on the right, okay? Much of the chapter is devoted to this 1 degree of freedom problem. This is a nice mechanics problem. The evolution as a function of time, and it's a continuous time axis, okay? So this is a mechanics problem in the usual sense. It's important to notice that it is a deterministic problem, okay? And the question, what is chaos? You can interview all these world's experts on what is chaos, and at the end of the day, you'll probably still be kind of confused. They don't have the greatest of rigorous definitions, but often you'll hear the phrase, the motion appears to be random, okay? You see, when we say that word appears, that's not really a highly rigorous term. The motion appears to be random. It appears to be, there appears to be no periodicity, and it's very sensitive to the initial conditions, right? We have this exponential growth of the initial conditions. Again, the butterfly effect. A butterfly in Tahiti with its wings in a different position causes a tornado in Kansas, so to speak. If you wait sufficiently, not immediately, right? You have to wait for this exponential growth. So that's the butterfly effect that's often mentioned here in the definition of chaos. And so those are really the two main things. The exponential growth, a tiny change in the initial conditions grows exponentially. So although this is a deterministic system, right, we know that it's governed by Newton's laws of motion. It is a deterministic system. But nevertheless, the crucial thing here with the chaos is you would, in some sense, need to know the initial conditions with infinite precision to really predict the long-term behavior. So the fact that the tiniest of changes to the initial conditions eventually, because of the exponential growth, gives you a completely different system. That's remarkably different here for the chaos. And then it appears to be random, right? There appears to be no recognizable structure, no periodicity. So that's kind of the definitions that you will hear for chaos. And again, we don't have a perfectly rigorous definition for what is chaos. Okay, in the case of chapter 5, right, this is very much on our to-do list for the final. We need to be very clear on the damp-driven oscillator. And let's take a second to write down the equation. So we had equation 5.57. Right, this was the differential equation that we were solving for the DDO, the damp-driven oscillator. we had our x double dot plus 2 beta x dot plus omega naught squared x. And at that point in the textbook, we described the driving term in the following way. Okay, so this is equation 5.57, right? And notice the structure here, this lowercase f naught, you see the dimensions are acceleration. So it's a little unfortunate that this is an f, which would remind you of a force. I guess the good news is it's not a capital F. It was originally a capital F as a force. Then we divided through by the mass. And so it's just understood that this lowercase f has dimensions of meters per second squared. Okay. So this is the equation, and compare that with what we got last time. Notice the structure. Okay. In both cases, for convenience, we chose the driving force to be proportional to the cosine of omega t. Right? We could have incorporated a phase shift here, but that can be reabsorbed into your choice of the origin for the time axis. So without loss of generality, we can simply declare that the driving force is proportional to the cosine of omega t. And again, this omega is the frequency determined by whoever is in charge of that. In the laboratory, we have some equipment. You typically have a rotating dial or something that allows you to choose this omega. It's logically distinct from the omega naught, right? This was the so-called natural frequency in radians per second of the oscillator. Okay, so the structure is remarkably similar. Down here, again, we have the cosine omega t. The crucial difference is that we have a sine here, a trigonometric function. So that's a nonlinear function. And here, it's just x to the first power. So that is a linear function. That's the crucial difference. Otherwise, the two equations are exact apart from this choice of terminology, choice of names really. Here it was f naught, and here we chose to introduce this lowercase gamma as a dimensionless quantity. Right? This makes it very clear. It's dimensionless. Right? In this equation, everything has dimensions, every term seconds to the -2. So this gamma is a control parameter. That's the language that is used for these chaotic systems. Okay, so now let's start to investigate. We mentioned the keyword here, the nonlinearity. Okay, the nonlinearity, when you take Physics 111A, for example, you'll build some audio systems that have some distortion. Right? A very good, faithful, audio system with a high fidelity, right, would produce a signal that has no distortion. So your output signal would be some multiple of the input signal. But here, the nonlinearity, right, the nonlinearity will give us some distortion. So that's one of the first things we want to understand. Let's look at this nonlinearity, okay? And this is an opportunity to review one of our foundation concepts, power series, right? Okay, here's our wonderful textbook. Here's the inside cover of our wonderful textbook. We got some series, and this one, there's the sign. The little z is to emphasize you can do this for complex numbers. Okay, so we have the sign of a number, and it's because of my focal plane is not optimal here. It's a little crowded under the document camera. If I can get this thing closer to the table, let's do this. Have I got a better focus? Maybe. Well, you see that's a z minus 1/3 factorial z to the third power plus 1/5 factorial z to the fifth power. And then there's a minus sign. So you see the pattern is clear at this point. The sign, that's the SIGN, the signs alternate, minus, plus, minus, plus. We have odd powers and odd factorials downstairs. That sums up our trigonometric function SIN sign. Okay, notice the hyperbolic sign. Very similar in appearance, right? It's a wonderful story. Okay, anyways, for the moment, we're looking at the sign, and the leading term, the so-called small angle approximation, The sine of z is just z itself. The first correction beyond that would be the minus 1/6 z cubed. Okay, so let's investigate the repercussions of that. All right, and we get to do some fun work with trigonometric identities. Okay, so a moment ago, we were speaking of the sine of z. In our problem, we're using the angle phi. That's pretty standard choice for pendulum. And now we're going to say, as we start to investigate what happens when the amplitude gets larger, we first look at the problem for extraordinarily small amplitudes and we recover the original material in chapter 5. What happens when we start to get to larger amplitudes? And that's a well-formulated statement, right? In the sense that phi is a pure number. It's not measured in meters, it's just a pure number, measured in radians. And when we say small or large, we're comparing to 1, unity. So for very small values, and here is the sine of phi. Okay, this is the so-called small angle approximation. If you'd like to improve upon that, you have the next term, minus 1/6. Okay, again, that's that formula right out of the book, inside front cover. And so let's truncate the series here. That means we discard all the higher order terms. So this is a better approximation than the usual small angle approximation, which carries only the first term. Okay, let's look at the implications for our problem. The differential equation that we were just looking at, we have a modified structure. We've got the phi double dot. We got the term with the first derivative. And now, you know, the next term is this omega naught squared times the sine of phi. Now we'll use this approximation. Okay, and this is equal to our driving term, which was the coefficient. There's the gamma. Okay, so the takeaway message is, as we explore what happens when we start to get to larger displacements, larger excursions away from equilibrium, it is this term here. Again, the non-linearity. This is a non-linear term because it's not phi to the first power. It's phi to the third. As long as it's an exponent other than 1, it's a non-linear term. Okay. The exception would be 0. If there's a constant, we know how to reabsorb that. But phi cubed, certainly a nonlinear term. Okay, now in this case, we can investigate a certain ansatz. Okay. So consider, okay, what we're going to do is look at a certain ansatz, and the fascinating behavior here is the so-called higher frequencies. So you know when you play musical instruments such as a guitar, you can pluck a string. If you pluck it at the center of the string, you tend to get mostly the fundamental, all right? And there are some of these overtones. These are notes that have a higher frequency. For example, twice as high or 3 times as high, et cetera, 4 times as high. And so those are called the overtones. The remarkable thing we're going to see later in today's lecture is we also have behavior at the so-called subharmonics. So half of the fundamental frequency, et cetera, and so forth. So we'll see how that emerges later. For this portion of the discussion, we're going to have this distortion. And so these will be harmonics in the usual sense. We're going to consider right? So this first term is very familiar to us from chapter 5, right? We know the so-called asymptotic behavior, right? The long-term behavior after the transients have died out, the initial conditions, you know, that decays away exponentially because of this beta, right? We do have some damping, so any information about the initial conditions fades away. And if you check back a long time later, you will see the system in a steady state solution with this kind of motion. All right, there is a phase shift, and we have a formula for that in chapter 5, and there's an amplitude. Okay, so having said that, this is the case again for chapter 5 without the distortion. Let's see if we can capture the leading behavior. Okay, so this is kind of an inquiry. We're going to look at this and notice the structure. The original term to this one is familiar to us from chapter 5. Right? We have omega t and there's a phase shift. Here, this second term, we have the same construction. Omega times t minus delta, that's the same phase shift, the same frequency. And as you know, this is the frequency of the driving force. We know the asymptotic behavior has the system synchronized, right? It's perfectly synchronized with the driving force. There is a phase shift, but we have this perfect synchronization. Right, so this, it's a higher frequency because of the factor of 3, but the periodicity, right? This is a function that repeats itself over and over again. The fundamental period of this thing, the entire thing, this is a periodic function. And the period, you know, we like to use tau for the period, is the 2 pi over omega. Okay, so if you draw a picture of this, you'll have the fundamental, okay, this cosine, and you see the frequency there, radians per second, so the period of that is 2 pi over omega. And we're thinking of this b as small. So small, if we say small, remember you must explain small compared to what? And we're going to say small compared to a. Okay. So that is to say, well, we could have dropped that absolute value sign there. This a is taken to be a positive number. So the absolute value of b is much less than the absolute value of a, which we could just call the a itself. Okay. So under that assumption, we can investigate the behavior of the system. The statement here about the periodicity is true even if b were large. B could be 10 times larger than a. This statement is still true because if you imagine plotting this function, it will repeat every so often, and the fundamental cycle on the time axis is this tau given by the 2 pi over omega, right? Because this function here repeats itself every 2 pi over omega. If for some reason you're only looking at this second term, it has a different period, right? It has a period of 2 pi over 3 omega. So the period is shorter. It's a higher frequency, has a shorter period. But again, the entire function still has this periodicity of 2 pi over omega. Okay. So again, the terminology that's used, this is the fundamental, and this is a harmonic. It's a higher frequency. It's an integer, 3 in this case, times the fundamental frequency. It's a higher frequency by an integer factor. So later in today's lecture, we'll look at subharmonics. That's the fascinating thing here. The sudden onset, as you crank up gamma from a small value, all of a sudden, there will be a subharmonic. You will see, especially, you could feed this into a Fourier synthesizer, right, which we do have in the laboratory. You can compute the spectrum, and suddenly you will see a subharmonic, so with half the frequency. But first, let's investigate this. This is a wonderful opportunity to bring in a trigonometric identity. Okay. And there are some wonderful trigonometric identities out there. Okay. Would you believe the cube of the cosine of x can be written as a linear combination of cos 3x and cos x with just some harmless coefficients? All right, so this is equal to, we got 1/4, we got the cosine okay. So that's an identity you can prove without too much trouble. You just, I would recommend starting with this term here and using angle addition formulas to express that in terms of just trig functions of x itself. And you can prove this rather easily. Okay, so this is important to us. We'll be using that term here. When you plug in this ansatz, okay, we're thinking of this b as small. So when we cube phi, that's what we must do. When we insert this into the equation, we must cube phi. We'll be getting the cube of the cosine, and that can be rewritten using this identity here. Okay. So in that sense, you can compute the distortion, right? As we move away from very small, right? We know from our work, right? Our work in chapter 5 is serving us well because we know if gamma is very, very small, we talked about gamma equaling 0, obviously the long-term behavior, phi would just go to 0. Now, if gamma is some very, very small number, then we can use our results from chapter 5 as a very good approximation. And remember, chapter 5 tells you the amplitude, right? For the long-term behavior, this amplitude is not a free parameter. It's determined by the amplitude of the driving force. Okay. Same with this phase shift. It's determined, we have formulas for that. Okay, so the question becomes, as we increase this gamma, all right, we're going to start seeing some distortion, and that's something we can compute here. We plug in, etc. Okay, so in terms of the physics of the problem, we want to appreciate how our knowledge of chapter 5 directly enters into the discussion here for these considerations with gamma very small, and then what happens as gamma gets larger. Okay, now the remarkable thing is the period doubling. This is the real surprise, that there's a threshold. Okay, so the period doubling. Okay, and what does this look like? And here's kind of the fascinating thing. It's interesting to visualize this. How can a small change, right? We mentioned there's a threshold. Wait a second. I'm getting a funny message here about the document camera connecting to audio, even though I told it not to. Yep, that can get a little annoying. I just want a single audio feed through the laptop. It seems like a reasonable request to me. Okay, so how can we visualize this period doubling? How can we visualize the threshold? Okay, so here's the picture. Okay, so as a function of time, suppose you have a periodic signal. It looks like this. Okay, so that's an impressionistic sketch. Okay, so let's say this is periodic, and you can read off the period anywhere in the diagram. So for example, I construct these two vertical reference lines to indicate this is a fundamental cycle. Okay, so on the time axis, the horizontal axis is the time axis. This is what we would call the period. So that's our lowercase tau. So the remarkable thing is, as you approach this threshold, as you increase the gamma by a very small amount, just a very small increase. What happens is every second feature here is slightly changed, okay? So that's the remarkable thing. How can you change a curve to suddenly have double the period, okay? It would be very drastic, okay? It would be very drastic if we simply drew a curve like this with twice the period, okay? That would mean we're doing something like this. Okay, so I've drawn a curve here with twice the period. So this picture does not happen. Let's just record that here. Does not happen. Because this would be a very drastic change. And here, of course, we're talking about our angle phi. We're interested in phi, and again, it's our continuous time axis. So this is a very drastic. If you change the control parameter, remember gamma is our control parameter. If you change it a small amount, and if you have a sudden change to this picture, this would be drastic. So that, well, I'll just remark here, drastic. So what does happen? How do we have this period doubling? Okay, what happens here, we think of our original picture. Here's the original picture. Okay, we draw something very similar. Okay, and again, I'm going to do an impressionistic sketch, so give me a second here. Okay, but what happens is every second, let's just focus our attention here on the bottom. Okay. So here's the key to this period doubling. This is slightly lower. Okay. This is what we call local minimum. You can compute that local minimum, and this is slightly lower than that one. And again, it's every second one. So this one here is slightly lower, and I did try to capture that. Okay, so that's the key to the period doubling. We have a period doubling. Right? Because now a fundamental repeat block, what part of this picture repeats itself? Well, you must use one of the lower ones and one of the higher ones. Let's choose this. Okay. So I've used the red color to indicate this is a fundamental block that gets repeated over and over again. And the crucial thing is we achieved it by a slight deformation of the original curve. So period doubling due to a small change in gamma, and it's a small increase. Okay, so that's the fundamental mechanism for the period doubling. Okay, then it turns out as you increase gamma some more, there's another threshold, and then the period doubles again. That means every fourth one of these features, you can think of slightly lower, slightly higher, and suddenly the period is 4 times greater. Okay, so many chaotic systems exhibit this kind of period doubling route to chaos. There are examples in chemistry with like a mercury cell. There are electrical circuits. And several decades ago, you know, this stuff was more popular. These things were widely available. You could purchase mechanical oscillators, carefully crafted, you know, these are precision instruments, but something like a damp-driven pendulum, electrical circuits, etc., And so the universality is remarkable. The idea that you have a control parameter, in this case, it was the amplitude of the driving force. And as you carefully tweak that amplitude, suddenly there comes a point where the period doubles, right? In the sense of there's a red block here. The fundamental repeat cycle is twice as high. Another way to say it is if you Fourier transform this signal, then on your spectrum analyzer, right, that's where you have a display of the spectral content. You can see all the frequencies. Suddenly, there will be a signal at half of the fundamental frequency. If you double the period, that's a signal at half of the fundamental frequency. So these are called subharmonics. So subharmonic. Okay. All right, so you see the frequency is 1/2 of the fundamental, so that's a subharmonic. That's in contrast to the usual notion of a harmonic. All right, so now what we want to do here, we've got the final exam on Thursday, right? And I did post some detailed information about the structure. It's going to be very similar to the midterm exam in terms of our logistics. The clock for your timer will be 3 hours and 15 minutes. You're supposed to work on your exam for 3 hours and then take your time for the next 15 minutes to prepare your PDF file. So for the remainder of today's lecture, we're going to do some review, all right, because we want to start reviewing for the final exam. The emphasis here during the review session is to take topics from different parts of the course and see how we can make comparisons, right? So we'll actually solve a problem in 4 different ways, all right? Yep, so the same problem, we'll solve it in 4 different ways. And this will be a nice opportunity to review material from different parts of the course. Okay, so here we go. As we do this, we're going to think back to something we've talked about, and actually, I think we mentioned this on the first day of the course, the so-called interplanetary superhighway, right? This also was part of this renaissance, right, in recent years. You can have spacecraft navigating around the solar system using much less fuel, okay? Much less fuel because of this so-called interplanetary superhighway, right? And so some truly advanced mathematics was used here. Right? And I mentioned that example, right? It got a little controversial. There was a space agency, not NASA, it was the space agency of a different country. I won't name the name of the country because they emerge as, quote, the bad guys in this story. But yeah, they had a spacecraft stranded with insufficient fuel to get to the moon. And some mathematicians, including Berkeley mathematicians, they used some very advanced methods, right? Mathematical methods. And they found a way to get that spacecraft to the moon. And now the foreign space agency attempted to prevent them from publishing this, right? They tried to get them to, I forget the terminology, but there's some legal terminology trying to prevent somebody from publishing something. So, yep, interesting story, a little bit of drama, etc. But yeah, using advanced methods, not the stuff that was known for hundreds of years, advanced methods, and again, the stable and the unstable manifolds. So our story today, as we review for the final exam, we're going to talk about the stable and the unstable manifolds. Okay. So, and then we'll solve the problem of finding fixed points in the analysis 4 different ways. Yep, it is amazing that we can solve this 4 different ways. Okay, so you'll recall we did talk about the pendulum, right? In chapter 12, we're talking about the pendulum with some extra forces. There's a damping force and there's a driving force. Let's talk about the pendulum once again. Just the simple pendulum itself. The pendulum, meaning you have a gravitational force, which provides a restoring force because of this mechanism with a pivot. And we know that the structure okay, the structure, you can look at state space, you can look at phase space. For this problem, the appearance is very similar. So let's look at, you see I made a very pronounced dot. Here's phi dot, okay? For the simple pendulum, this picture, which you recognize as state space, this is the classical state space. It has a structure. If you need to draw this picture quickly, here's what I recommend. Draw the separatrix. Okay, and you know that the separatrix, we also have the mirror image like this. So here I go, I'm drawing the mirror image. What are these points? As you know, the separatrix, these are the points in this picture where the total mechanical energy is exactly equal to the energy of the system when you're at the unstable equilibrium, okay? So there are several foundation concepts in that statement I just made. There are several foundation concepts. The total mechanical energy, all right? In this case, the Hamiltonian is the total mechanical energy, right? We did draw the classical state space. You could equivalently put a p-axis here for this problem. P is just a multiple of phi dot, so those are equivalent. The pictures are identical. So you know we introduced the Hamiltonian in chapter 7. It was a function of q and q dot, and for this problem that's phi and phi dot. Perfectly valid thing to do. You can, and we did this in chapter 7, you can define a Hamiltonian, which is a function on the classical state space, and for this problem it's just the total mechanical energy. Okay, this curve here, it helped me to draw it as two separate sine, actually I should say cosine waves, right? Because look at the behavior at the origin. So that's a quick way to draw it. These are the points, right? It is meaningful to make the following statement. These are the points in this diagram where the total mechanical energy is equal to the energy of the pendulum when it is balanced at the unstable equilibrium. So H equals E at the unstable equilibrium. Okay. Sorry, I wrote it so small it's hard to read. But this is a very important equation. It's valid both for state space and for phase space. In chapter 7, we talked about state space, in this case, phi and phi dot. It is meaningful to talk about the Hamiltonian and the set of points where the Hamiltonian is equal to, right? The Hamiltonian, we must understand, is a scalar field defined on this space. The set of points where it is equal to the energy, right? At the end, in particular, if you're right here, let me put it this way. If you're right here, this is the pendulum balanced and motionless, right? It's motionless because phi dot is 0. Where I'm holding the pen, phi dot is 0. And the angle is pi. Might as well label this, right? This is pi. I'm going to draw it small because we'll draw some more stuff. Okay, so that's important. You draw the separatrix. Now, I'm going to draw some more level sets, right? That's a term that is used. Equipotentials for different values of the total energy. And now, I must be impressionistic. We don't have time to draw detailed pictures. We got to crank this picture out. Okay. And then we have the so-called rolling motion. If the energy is greater than this value, the E unstable, then you have the rolling motion. If it's slightly greater, you can go clockwise, you can go counterclockwise with the rolling motion. Yep, and like I said, impressionistic sketch. Okay, so that's the picture. Once again, we have the classical state space These are the crucial constructions, the mathematical construction. First of all, this space. Next, the Hamiltonian is a scalar function. And when you write this equation, you can identify all points in this picture for which this is true. And therefore, I should put a dashed box around this because I indicated those points in the picture using a dashed line. So therefore, I should put a dashed box. It makes for a very clear, this becomes a legend, right? This becomes a legend for the picture, all right? So we're interested in stable and unstable points, okay? We know that the pendulum here, here's phi equals 0 and phi dot equals 0. That's the equilibrium when the pendulum hangs straight down. That's stable. So this is this, I'll draw a dot there. That dot indicates a stable equilibrium, and this dot indicates an unstable equilibrium. Okay, those are two very important features. Now here, we have this unstable equilibrium. We're going to investigate the behavior of the system near the unstable equilibrium, and our goal is to understand something called the Lagrange points. Okay, now this is logically different. It's a different subject. Therefore, I put a big horizontal line across the picture. The similarity is we're going to have a discussion about unstable points. We'll have a discussion of stable points and a discussion of unstable points. All right. And as you know, we looked at those slides earlier in the semester by Kathleen Howell, and the key thing was this notion of the L1 gateway near the moon. Okay, if you can get your spacecraft to that L1 gateway, give it a little push onto an unstable manifold and it will go sailing through the solar system, right? Similar story here. If you look at these critical points, right, here's this equilibrium, it's unstable. If you look at the separatrix, we'll see that there are two directions, going to the upper right and going to the lower left. You have exponential growth away from the critical point. And there are two directions, the lower right and the upper left, you have exponential decay towards the equilibrium, okay? So we're going to investigate that. And again, our motivation is we're looking ahead to the Lagrange points. We're going to study the Lagrange points, right? This is an exciting topic here for the motion of objects in the solar system, including spacecraft that someday you will design and put into orbit, okay, and put on their journey throughout the solar system. So we'll go through this discussion. We're going to analyze this picture in greater detail. We're going to look at stable and unstable points in this picture. And then we'll look at a different problem, right? Lagrange points. This is a different problem, not the pendulum. This problem was the simple pendulum here. This is the simple pendulum. Right? The simple pendulum, though it is simple, it's still a very useful problem to appreciate scalar fields such as the Hamiltonian. It's a function defined on state space. It's also in the Hamiltonian view, it's a function defined on phase space. And there are vector fields. I haven't drawn the vector fields. This picture would get messy, but we know the vector field for Hamiltonian evolution is a vector field that's everywhere tangent to these curves, because these are curves of constant total mechanical energy. And the dots are special degenerate cases, right? That when this curve shrinks down to a single dot, that's the stable equilibrium. And this single dot, that's the unstable equilibrium, okay? So the vector field is 0 here, right? And the vector field is 0 here. So it's that vector field which is crucial to appreciating Hamiltonian mechanics, that you have a vector field defined on phase space. And the vector field governs the evolution of the system. These curves are the so-called streamlines. They're everywhere tangent to the vector field. So the curves, as we've drawn them here, they don't tell you how quickly or slowly you move along the curve. But we know that the evolution of the system must respect these curves. It must stay on one of the curves. You, as the experimenter, when you prepare the system, you start it somewhere in this picture, maybe right here. And then it evolves according to the vector field. It will stay on one of these curves. Okay, so let's analyze the behavior. We'll start with this near the origin. That's something we were talking about a moment ago when we talked about the pendulum, right? We talked about the small angle approximation. Small angle approximation, there it is. So let's investigate this vector field near the origin. Okay, here we go. We're going to investigate the vector field near the origin. Okay, so near the origin, we're going to look at this portion of the picture near the origin. Here's our picture. Okay, the vector field swirls around like this. Okay, we got to budget our time. That's all the time we have to draw this vector field. Maybe one more little arrow like so. Okay, so this is the vector field. We're looking near the origin, and this is the actual vector field. What does that mean? Well, we have a vector field V, right? This is telling you how quickly you're going to move in state space. That's the vector field. And so okay, this is the formula for the vector field. Why is that true? This is the velocity of the system. So what does that mean? Well, this is ddt of our position. What's our position in this space? Again, this is state space, and our position in state space is phi dot. Okay, so let's be very clear. This is our location in state space. So the phi, you can see it right there on that axis, right? That's the phi, and the phi dot. Here we go with phi dot. Okay, that's why I went to all the trouble to draw these red arrows. I want to emphasize phi, comma, phi dot. Those are our coordinates, and that's why those occur here as labels on the axes. So this vector is our position in the classical state space. The time derivative of our position in the classical state space is the velocity vector field in state space, right? So this is our velocity in state space. Velocity in state space. Okay, that's our velocity in state space. And obviously phi dot is just phi dot, right? In other words, here we need a prescription. How do you compute this velocity vector if you have these two numbers? Well, the first one, you just use the number phi dot, put it right there. The second one, that would be phi double dot, right? ddt of phi dot here, that's phi double dot. And phi double dot, because near the origin we have the small angle approximation. Voila, small angle approximation, okay? So near the origin we have this business. Okay, so that's our vector field, and we can write this as a matrix, okay? So this vector field is equal to a matrix, and that matrix is a 0, 1 minus omega naught squared 0. It's a matrix times our same vector. This is the same vector, the phi dot vector. Okay, so this is the key to solving the problem. You know from Physics 89, also in the past Math 54, you know how to solve this, right? We have a coupled system of differential equations. The result here is we swirl around, right? We have these closed orbits. So closed orbits, stable. The key words here, closed orbits. Closed orbits. They are stable. If you give the system a little kick, it stays near the equilibrium. Stable. We stay near the, you see how we stay near the, you give it a kick, no problem. We're going to stay near the equilibrium just on a different closed orbit. And periodic. Okay, so that's the situation near the origin. All right, nice summary. That was near the origin. And again, we're looking at this picture here. Okay, we just analyzed this region near the origin. We zoomed in. Here's the picture with the vector field. Here's the analysis. The remaining task, matrix exponentiation, that's covered in Math 89, or you can just solve the differential equations. That's equal. Let's look at this point. This is an unstable equilibrium. Okay, so the structure of this discussion will be similar. The title, near. Now, for that discussion, I just used the word origin. That describes this point here. And near the origin, this region around the origin. Now we're going to be near, and of course I will use the coordinates in the picture. So our coordinates phi comma phi dot this is an unstable equilibrium. Okay, let's draw the vector field. Again, we'll have a very similar diagram. So here's our picture with a phi and a phi dot. Okay, so near that point, I'm drawing a picture. We're zooming in on this point here. Okay, so nearby the separatrix just looks like a diagonal line like so. That's the separatrix. Okay, and we're going to see these vectors come in, some small vectors like so. These are small vectors. If you're near the critical point, these are very small vectors. Remember the intermediate axis theorem. Oops. Now let's do this. Sorry about that. And over here, like so, we have talked in the past about the intermediate axis theorem. If you're near this critical point, the vectors are very small. The evolution of the system is slow. Okay, the vector field over here looks like this. Obviously, it's a very cool vector field. You have this nice structure, and all of these are small arrows when you're near the unstable equilibrium, like so. If you get further away, the arrows get larger. The same was true earlier in this picture. Further away, the arrows are larger. All right, now we don't have time to draw arrows all day, but here I claim I've captured, this is the structure near a critical point. So notice this surface, this is the unstable manifold. Because you see the system moves away. So this is the unstable manifold. Because the system moves away from the equilibrium, it grows exponentially. This one is the stable manifold. Maybe we should go with pencil for this. This gives us a different color. So this one is stable, right? You can see the vector field goes towards. So this is the stable manifold. Okay, so that's the structure we see here at this critical point. The critical point is in the center of that picture. We have the stable manifold where you move towards the critical point. That's true here. You're moving towards a critical point, towards a critical, and here you move away from the critical point on the unstable manifold. The vector field, again, we have a very similar story. This matrix is now looking like this. We have a 0, 1. And we have a sign reversal here. This minus omega naught squared is now plus omega naught squared 0. So that's the only difference. The structure is the same, phi dot, right? We have a vector field. In both cases, the vector field is given by a constant matrix times your position. A constant matrix times your position. Here I should say relative to, so subtracting out this is relative to the equilibrium. Okay. But the crucial thing is the matrix, here you had a minus sign, here you have a plus sign. That is the mathematical reason for why you have a vastly different structure. In this case, the vector field swirls around the equilibrium point. In this case, you have this structure with an unstable manifold and a stable manifold. Okay, so that brings us to the end of our hour. We'll talk some more about this next time. We wanted to talk about the interplanetary superhighway. You remember from those slides, we talked about stable and unstable manifolds. So here for the Humble pendulum, we've seen that we do have stable and unstable manifolds. And in our next meeting, as we continue the review, right, we are reviewing topics for the final exam, and these are useful exercises. So I'm going to stop the recording. Let's see, we click on this thing.